Hello viewers, good evening. Yeah, this is making physics simple with Idia. I'm so excited coming your way this evening. Or once again, today we are going to continue with the concept or the topic under discussion, simple harmonic motion (SHM). Now we are going to look at another aspect of simple harmonic motion, which is the simple pendulum, the motion of the simple pendulum. Yes, when we're talking about examples of simple motions we can describe as simple harmonic, we made mention of the motion of a simple pendulum. Okay, so we are going to today look at what makes the aspects of the simple pendulum, which actually makes it simple harmonic by nature. Okay, and these are what we are going to look at. So stay tuned, relax, and then as I take you through the concept of a simple pendulum. When we talk about a simple pendulum is basically any mass connected to a string and made to oscillate at a fixed point. So any mass. Okay, in the laboratory we often have a metallic ball mass attached to a string and then tied on the gyrator stand. Okay, and then made to oscillate. But when we talk about a simple pendulum, it is basically any mass connected to a string and made to oscillate at a fixed point. And this is an example of a simple pendulum. This is the mass, this is the string. Okay, then we tie it to a fixed point. Now when the mass is given small angular displacement in one direction, it moves to and fro around a fixed imaginary point, which is this. So let's assume that initially this is the fixed point. Okay, let me put it on the board. If we are assuming that initially okay, so the arrangement we have on the board, okay, depicts a simple pendulum. This arrangement depicts a simple pendulum. Just any mass connected by a string and made to oscillate about a fixed point. Okay, so this is a simple pendulum. Okay, with the weight length of the string. Now, when the object is displaced from the mean point, this point where the stationary point is what we call as the mean point, or the rest position. The main point, the rest position, or the equilibrium position. At the mean point, the net force acting on the object is equal to 0. Okay, and that is why the object isn't moving in any direction but is at a rest. Now when the object is displaced through a small angular displacement theta and the left, the object oscillates around the mean point. Okay, so let's see the object being given that small angular displacement. Let me give it that small angular displacement theta. Good. So when the object is given that small angular displacement theta, okay, what happens is that, let me also draw a small angular displacement theta here. Okay, so when the object is given that small angular displacement theta, either this way through a displacement, this, or through this displacement, this, from the main point, what happens is that the object moves, okay, back and forth around this fixed point, O. Let's label the fixed point to be O. Okay, so when the object is given a small angular displacement, it moves to and fro around the fixed point O. Here, because it is gliding on the surface of the board, that is why it doesn't oscillate much, and it will stop oscillating within a short time. Friction. Okay, there's external force acting on it, which is friction, which is reducing the speed of it. Other than that, if it's in the air, you see it oscillating just like that. So assuming the object is here and I displace it in one direction, okay, you see it moving back and forth. Okay, and how did we define oscillatory motion? How did we define oscillatory motion? Is the repeated to and fro movement of an object, okay, or a body around a fixed point or a mean point or equilibrium position. Okay, so the motion of the simple pendulum, clearly from the illustration we see is a type of oscillatory motion, which is also an SHM. Okay, how did we define SHM? We said that simple harmonic motion is the repeated to and fro motion of a body whose repeated to and fro motion of a body around a fixed point whose acceleration is directly proportional to the displacement and is directed towards the fixed point or the mean position. Okay, so for SHM here, its acceleration is directly proportional to displacement. Its acceleration is also always directed towards the fixed point. Okay, so these are the key elements which defines a simple harmonic motion. And so if we are classifying the motion of a simple pendulum, which is this, and then the motion of a loaded spring, this is what we call the arrangement or the system we call as a loaded or weighted spring. Okay, this is the spring, and then it is loaded at one end. Then whenever the spring net force or external force is applied in stretching or compressing the spring. Look at what happened. Okay, just small displacement, and we have the back and forth movement of the object or the mass around a fixed position. So this is what we call a loaded or the weighted spring. Okay, either you stretch it or you compress it and you leave it, you see the oscillation of the mass. Okay, so this is simple harmonic. Okay, all right. So we have the loaded spring and then the simple pendulum. Today we are only looking at the motion of the simple pendulum. Okay, and then we shall see why do we describe it as simple harmonic motion. All right. Okay, so this is the simple pendulum. Okay, now this is the object having been displaced from its main position O. Okay, I'm shading the mass so that it will be differentiated from the fixed point or the main point O. This is the main point O. The object is given a small angular displacement theta, and when it is left, the object moves back and forth around a point O, oscillating. Okay, now when the object is displaced in this direction, okay, the object moves to some point and gravity acts on its mass, okay, and it's restored. Okay, but when it is returning, because it has momentum, okay, it crosses its equilibrium position or the main point, come to the other end, gravity acts on it and then restored. Okay, and as a result, stay put in between these two extremes. That's okay. Alright. Now let's look at what makes this motion simple harmonic. If it has all the qualities we need to see in simple harmonic motion. So let's extend this tension vector. It is displaced from its equilibrium position or main point through a small angular displacement. Let's extend the weight vector. Let's extend the tension vector. Tension is vertical, perpendicular to the horizontal because of gravity. The weight of the object. Okay. Now what we also realize here is that, okay, so when we extend the tension vector, okay, we have this angle corresponding with this angle. Okay, or when we extend the weight vector, we go. So either we realize that, okay, this angle corresponds with this, or we extend the weight vector and then realize that this alternates with this, and if this angle alternates with this, then it also vertically opposite to what is here, and so this is also theta. Okay, so what we have is that we see the weight, okay, looking like shifting by an angle theta, but actually the weight doesn't shift because it's due to gravity, and gravity will never shift. Okay, but per our consideration of this vector and this vector, it looks as if this is skewed by this magnitude. Okay, so when we resolve to get components of this weight, because it is skewed at an angle theta, we have this side being the adjacent, this vector, a standard version of the tension being the adjacent to the angle. So the adjacent is mg cos of theta. Okay, and then the side which is opposite to the angle, which is this is mg sine theta. Okay, so if you perhaps you don't see it well, let me redraw it. This is mg, then this is the angle of tilt theta. Okay, because this side is adjacent to the angle, when we resolve it using trigonometry, a right angle kind of triangle, we have the adjacent giving us cos of theta is equal to the adjacent, which is this unknown component divided by the hypotenuse mg. Therefore, the unknown component is mg. Let me shift my screen a bit. The unknown component becomes mg cos of theta, and that unknown component is this. Okay, now the opposite component, okay, can be determined using sine of the angle theta. Sine of the angle, let me bring it down. Sine of the angle theta, which is equal to the opposite unknown divided by the adjacent, which is mg. Therefore, the unknown is equal to mg sine theta. Okay, which is this component. Okay, this is mg. This is mg sine theta. Okay, so that is how this thing actually looks like. Okay, let me put this. When we resolve a weight vector, we realize that we have the horizontal component as this, yes, and then the vertical component as this. Now, per equal vector approach, instead of us having this component over here, vectors are said to be equal when they have the same magnitude, direction, and are parallel. So you can redraw this along the object to direct it here. So this component is mg sine theta. Okay, per equal vectors approach. Now, when we look at the forces or the component existing in equilibrium. When we look at along this component, all right, we realize that mg cos theta component is balanced by the tension in the spring. So this component mg cos theta is balanced by, so these two vectors or forces, okay, we say are in equilibrium. So mg cos theta and the tension T in the string are therefore in equilibrium. And we all know at equilibrium the net the net force acting on the body is 0. Okay, so when you consider the forces acting on the body around this plane, you say there is equilibrium situation over here. Okay, now when you look at it around this line, okay, this component mg sine theta is unbalanced. So there is no component of forces balancing the object here. Okay, there's no component balancing the force. This vector components over here. Okay, and so this is what is responsible for causing the restoring of the object back to its original position. So this is what I'm trying to illustrate. A minute. When the object is displaced, okay, when the object is displaced, the mg sine theta component is responsible for restoring the object back to its original position. So you displace it in this direction, then because this component mg sine theta component is not balanced over here, it causes the movement or the acceleration of the body to its original position. Okay, so the restoring force which always brings it to its mean point, to the direction of its mean point, is this. So we say that restoring force is equal to mg sine theta. Okay, why? Because the mg sine theta component is unbalanced. Okay, an unbalanced force, always causes an acceleration or movement of a body. So the unbalanced force, which is mg sine theta component, is always what is responsible for bringing the object back to its back to its original position. So you displace it, the mg sine theta component restores it to its original position. Okay, so when it comes to this point, when the object comes to the other far end, okay, you move from here and come here, the same component, the mg sine theta component, always will restore it to the direction of the mean point O. Okay, when it comes here, because it is going up, the mg sine theta component restores it on, and it is left to oscillate between these extreme ends. Okay, so what the force which is always responsible for restoring it to its original position is the mg sine theta component, the restoring force. Okay. So we say that restoring force restoring because the restoring force is equal to that. Yes, a restoring force would always cause the movement of the object or the acceleration of the object. So what is the acceleration of the object when it was acted on by the restoring force? So let's look for acceleration. But for Newton's second law, we have F is equal to mass times acceleration. Therefore, the restoring force, which is ma, will be equal to mg sine theta component. Okay. And this here, the restoring force is negated because you see we displace the object in one direction, and then the restoring force also acts in the opposite direction. So when the object is displaced in this displacement going here, the restoring force will come to the direction of the first point. When the object is displaced this way and then left, the restoring force acts oppositely. So the direction of the displacement and then the acceleration or the restoring force are always negative. That's why we are negating the restoring force. Okay. Therefore, the acceleration is equal to minus g sine theta. So this is a relation for the acceleration of the body. So this is the extent to which the object accelerates to the direction of the fixed point O. Fixed point. Yes. So if you want to calculate the acceleration, is equal to gravity times the sine of the angle of displacement theta. Okay, that's the relation for the acceleration of the body to the fixed point. All right. Now I want us to, you see, here we are dealing with a body moving, okay, oscillating at a certain constant angular velocity. Okay, so we are dealing with an angular measurement in radians. So when you have sine of small angle theta, sine of small angles in radians, this is always equal to the angle theta. So sine of theta is approximately equal to theta in radian, meaning the angular measurement must be in radian. That's why we only give a small angular displacement, because we want to obey this rule or satisfy this condition. Okay, so if the sine of small angle in radian is equal to the angle, then over here we have A equal to minus J theta. A equal to minus J theta, because we've considered small angle theta. Now when we look at this, okay, if we look at it in terms of length, or yes, length of the string and then small angular displacement, and not in terms of forces, this is equal to the length of the string, this is equal to the radius of the circle, that is the radius. And so when you take the sine of this the sine in terms of the length of the string and radius, we realize that sine is equal to r on the length of the string. Okay. All right. Sine is equal to, let's give this as not as radius but displacement y, small displacement when the object is displaced, so y instead of the radius. Sorry, because it's not moving in a circle, not moving conically, we will consider the displacement and not the radius. Okay, so sine theta here is equal to, and here sine of small angle theta is always equal to the angle in radians. So theta is equal to y on L because sine theta is equal to theta in radian. Okay, let's use this end of the board. So if theta is equal to y on L, then I can say that the acceleration E is equal to minus g y on L. Okay, now because G and L are constants, yes, G is gravity, L is the length of the string, it can always be determined. So G and L are constants. So we can write the acceleration as minus k y, where k is equal to G on L. Okay, and so if A is equal to minus ky, then we can see that the acceleration is directly proportional to the displacement. The acceleration is also satisfying the condition for a body in simple harmonic motion. Okay, that its acceleration should be directly proportional to the displacement. The acceleration should be always directed to the fixed point, meaning the direction of the acceleration and then the displacement are always opposing. Okay, so once we've gone through this and we have satisfied this important condition for simple harmonic motion, we have confirmed that the motion of a simple pendulum is simple harmonic in nature. This is the key fact about the motion of a simple pendulum. Okay, once we say that the motion obeys simple harmonic, the attributes or features of simple harmonic motion, then we have to see this important information. Okay, now there's another important fact we can, or information we can retrieve, and that is the period of oscillation, the time taken for the oscillation. Okay, the time for one complete oscillation, the period. So let's look at how to obtain the period of oscillation of a simple pendulum. The period of oscillation of a simple pendulum. That's another important point to look out for. So period of simple pendulum. Now when we look at features of the simple pendulum earlier on when we started the whole topic, we saw that the acceleration of a simple pendulum is given by minus square of the angular velocity times this, if you recall. Alright, now here, what expression did we get for the acceleration? The acceleration A is equal to minus G on L times Y. This is general SHM relation for A. General SHM relation for A, and this is E for A, acceleration for simple pendulum. But when you compare or equate, we can have omega squared minus omega squared y being equal to minus J on L y. Y will cancel out, and then the negative will also cancel, giving us omega squared is equal to J on L. Okay. If omega squared is equal to J on L, then what is omega? Or omega obviously will be equal to the square root of J on L. Now, because omega is equal to 2 pi Am divided by the period, we can say that we can substitute 2 pi on T for omega, and we have this J on L. Yeah, let's try and then make T the subject. When we create space here, let's make T the subject. When we reciprocate this, the left hand side we have T on 2 pi to be equal to square root. Then we have to reciprocate the right hand side to L on G. Okay, so when you take the reciprocal of the left hand side, you have to take the reciprocal of the right hand side as well. When you make T the subject, you have 2 pi times L on G. Hello? This is a very important relation we use in mechanics, which is the period of oscillation of a simple pendulum. Okay, the time taken for a simple pendulum oscillating to make one complete, okay, or the time for one complete oscillation from here depends on, okay, is directly proportional to the square root of the length, because apart from the length, the rest are all constant, meaning that if you have a simple pendulum, okay, the time for a complete oscillation depends on the length measured from the center. If you vary the length, the period also varies. So the only variable here is the length, and it depends on the time for a complete oscillation depends on changing the length. If you increase the length, it will also increase. If you decrease the length, it will also decrease in that order. How do we, this concept is applied so much. Example, you see in factories and some restaurants, we have recessed lights or lights that are always suspended from the roof to the working plane. Okay, the light is always suspended from the roof to the working plane. Assuming one is asked to determine the length of the wire or of the conductor from the ceiling top there to wherever it is. Okay, you can apply this concept of simple motion of the simple pendulum to determine. And how do you do that? Yes, we are talking about a wire connecting a bulb. Let's assume the bulb is one of these fluorescent tubes. Okay, and this is the working plane. So from the ceiling, there is the ceiling to the working plane. The working plane is somewhere here. We are asked to determine the length of this wire connecting from the ceiling, and usually from the working plane to the ceiling so long that you can't use a ladder to measure. So as an engineer or a physicist, what will you do to determine this? So what you do is that you hold, this is an arrangement you call as a simple pendulum. You hold a mass and then give it a small angular displacement, and you determine the time for maybe a number of oscillations. It can be 20. So what I'm trying to say is similar to this situation. Okay, this is the conductor, this is the lamp. So you displace it and then count for a certain number of oscillations. Okay, so as you displace it, 1, 2, whilst you are timing. So the moment you display, you account, maybe you want to count a certain number of complete oscillations. The choice is, so it can be 10, it can be 20, but you will at the same time determine the time for that number of oscillations. So the moment you displace it, you start the timing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you stop the watch. So what do you have? You have n number of oscillations. N is equal to number of oscillations. You have 10. Then the time for that number of oscillations is what you determine using the stopwatch. So x. Okay, so you have x seconds for 10 number of oscillations. So how do you determine the period? And the period is the time for one complete oscillation. Period, okay, is equal to time divided by the number of oscillations. Therefore, your time is x seconds divided by how many oscillations you have? 10. Okay, so you have the time for one complete oscillation being x on 10 seconds. So how then do you determine the length? Using this relation, t is equal to 2 pi and the square root of L on G. You know this is t, and t is this. So x on 10 is equal to 2 pi L on G. Then you make L the subject, since that the length is what you are looking for. So you have we have to square both sides of the equation. So x squared, x on 10 all squared will be equal to 4 pi squared L on G. L therefore is equal to 3 times x on 10 all squared divided by 4 pi squared. Okay, so the length of the wire you are asked to determine as an engineer will depend on J is constant 9.81, okay, x squared over 400 pi squared. I mean I've squared 10, it gives me 100, but it will come down to multiply 4, that's why I have 400 here. So what we are saying is that L, the length will be equal to 9.81 times, then you have x. X is the time for that number of oscillation. So when you substitute whatever you got into here, divide by 400 pi squared, you have the length, because the only J is constant, pi is constant, the only changing variable is the time, which you were able to determine using the stopwatch. So this is how we can apply this concept of simple harmonic motion, the simple pendulum, for that particular purpose. Okay, and so we have been able to prove that the motion of a simple pendulum is simple harmonic, because as we went through, we realized that its acceleration is equal to its acceleration A is equal to minus G on Ly. Okay, and this, because G is a constant, the length is also a constant. This is the constant part, and so we conclude that its acceleration is directly proportional to the displacement. Its acceleration is always directed towards the main point or the rest position. Okay, which are the two main attributes of SHM. There we went on to calculate for, derive the formula for the period of oscillation of a simple pendulum and how it is applied in solving problems. Okay, all right. So this is the simple pendulum. In our next discussion, we will be looking at the loaded or weighted spring. We are saying that the motion of this is simple harmonic. So if it's simple harmonic, then we have to get its acceleration being directly proportional to the displacement, and its acceleration always directed towards the fixed point, which is another key important. So that is the next thing we'll be looking at, the loaded spring, or the motion of the helical spring to indicate or denotes SHM. That is our next thing we are going to look at. Thank you so much for joining me today, or welcoming me in your various homes. We'll meet once again to look at the other aspects of SHM, which is the loaded spring system. Alright, bye bye and see you. But please do not forget to subscribe, share, and then pass your comment. I need that so badly. Thank you so much. Bye bye.